Hello and welcome to Any Combo Lords. Sorry, it took me a moment to get my camera going. We had to do today's math lesson slash live stream question and answer in the bedroom that I technically do sleep in. I don't sleep in the combo classroom, believe it or not. So, unfortunately, not going to be able to access all the combo classroom stuff right away. Luckily, we're still going to make things work. I'll show you how in a minute. Now, on a nice rainy day, which right now it's not going too hard, but it's going to be going on and off all afternoon, I still have all my whiteboards and stuff out there. Tried to tarp up the combo classroom so not too much was being destroyed, but hard to say. We'll have to check on it later. But I didn't have my whiteboard. Good time, maybe, for me to have gotten this mysterious package. What could someone like me possibly have ordered? I also realized right before the stream that this package had my address on it, but I took it off, so it's not on there now. Now, opening this package, we'll see. Yeah, too much tape. Okay. What we'll see is that despite me having left my numerous little whiteboards and my big whiteboard out there, I now have a medium whiteboard. That is the type of thing a person like me would have ordered. More whiteboards. Is it super dark for you guys for some reason? Here it says someone said it's dark, but hopefully looks all right. What's the time here? It is just almost noon, almost the 12 o'clock that's called PM, but it's always confusing because it's right on the other side. Now, someone said we now have the same number of whiteboards. I would doubt that because I have a lot of the little ones. I have probably 40 miniature whiteboards, so I'm not positive that you're going to have that many. However, maybe we have the same amount of medium to large whiteboards. So this will come in handy. Additionally, not only will this whiteboard come in handy, but I got another whiteboard related thing, which is smaller sheets of whiteboard graph paper. Now, that's going to come in handy. Graph paper that you can write on and erase. And this is going to be what we will use for one of our first mathematical activities. I'm not sure why it's dark for you guys. It looks light to me, but let me check real quick by pulling up the stream from another tab to see what it looks like for you guys. Yeah, I think that may be as bright as we get right now. It's not hyper bright. I don't have the sunlight on my side. Still working on getting good gear to get this zone set up for streaming more often. But for now, we will have an impromptu one using our little graph paper to look at some cool shapes I've been messing around with. Now, often a lot of the topics I like are kind of what you could call number theory. But sometimes number theory, when you study integers and patterns with those, sometimes verges towards some fun geometric things as well. So it's good to have a few interpretations for things, like if we're wondering what builds up numbers multiplicatively, like how every number has a unique prime factorization, like 12 is 2 times 2 times 3. What are some different ways we could visualize that? Now, sometimes I've done examples with times tables, and we might get kind of times table-y here, but let's start out with treating this like the grid that they want it to be. Now, of course, feel free to leave any questions because I did also call this a question and answer because by some marvelous, awesome chance, we are up to 70,000 combo lords here. That is awesome. Thank you all so much. And for now, what I will be mostly focused on is showing some math shapes that I'm sure at some point I'll end up turning these into some full episode once I've gotten a bunch of them worked on with like some animators or programmers or stuff. But right now we can hand draw some stuff, and we're going to run out of room once we go past that line. But this gives us 12 on each X direction and 10 on each Y direction, and that'll be enough to start. Now, let's say that we're treating this like the positive X numbers, negative X numbers, and this is a Y axis, kind of like when you often graph, like if I were to have graphed Y equals, how about this? We're going to say we're graphing just the points where X plus Y equals 0. So here we get one. That's a freebie. So someone wants more lights. It didn't look that dark when I pulled up the stream, but I can try and move a light closer. So one sec. All right, how's that? So here we got our dot of our pretty obvious one, where here we're going for the grid points only. We're not graphing a whole line. We're just looking for grid points where X plus Y equals 0. So now we can check when X is 1, if Y is -1, that works. And all of these ones going that way work. We could keep going. All these ones this way too, when X is negative and Y is the same amount but positive, those work. So here we would get a bunch, going infinitely, of little lines or dots on a line. Now, even if I had them equal something else, like X plus Y equals 10 or something, it would still be a linear shape that they all landed on, straight. And that's because when we play with addition in that way, it's more likely to be straight. But what if we went to multiplication, and if I said all the spots where X times Y, all the grid points, remember, where X times Y is 0, well, that one's a little more boring because we basically get the ones where one of them is 0. You need one of them to be 0, so we get all the spots there. But what if we said all the grid points where X times Y equals 6? Well, now let's think about this. Now, if I have X is 1 and Y is 6, that'll work. Same with 1, 6. Now, we're not going to be able to make any in this quadrant, but we are going to get a mirror in this quadrant when they're both negative. They're either going to need to both be positive or both be negative to hit that positive 6. So we're also going to get -1 times -6, and that over here. Now, when we go back to thinking about these as factors of numbers and relationships that'll pop out there, these are just sort of a mirror image of the factors that we're going to draw because they're going to look cool. But as far as factors are concerned, that's this region. So now we're going to look at what other points could land on there. It's not just 1 times 6, but you could also make 6 with 2 times 3. So we get these ones. So there we go. Now, we can sort of see that these aren't linear. There's something a little more than linear going on there. And so, and to whoever's asking about the imaginary plane, yes, it's or we often call it the complex plane because it has real too. Yes, this will be used at some point to demonstrate that axis being imaginary. But right now, they're all real, just 2 variables. So that was 6. What if I say that we're going to instead do 12? now we're going to have a little more going on. So we're going to get, well, 12 doesn't fit on that direction. So 1 times 12, you're going to have to imagine its mirror dot up there. We're also going to say just imagine this is going to be a reflection of it. But let's see what else pops up here that are basically the factors of the number, because we end up hitting any grid point where x times y equals 12 is going to represent one way of factoring 12 into positive integers. And that's really what factors are, like two positive integers, but you call just either of them the factor, but you need a pair with it to go there. Although in square numbers, it could be paired with itself. So here we have 112, and then we get 2, 6. That's 5, 6. And we get 2, 6 here. And remember, we would have gotten the 12 up there as well. So imagine the dot up there on 112. Then if we want here, we could say 4 times 3 has 2 spots where that could fit. 4 times 3 and 4 times 3. And now we're getting this even bigger swoopy curve. If there is one up there too. So what's going on with these swoopy curves? Well, one thing that's going on with them is that when I say x times y equals 12, if I graph that in a more typical way, I would isolate the y and we would end up with y equals 12 over x. And that's going to look something like this, we can tell. And it is going to have that whole curve, and it would have a mirror curve here too. But we were just looking at, does it hit a bunch of grid points or not? So we can tell that if we play this game for does x times y equal some number, it's going to have a swoopy shape, but how many points it touches will depend on how factorable that number is. So now let's say we take this game one step further. We're going to say that for 12 here, first what we're going to do is put the 12 dots back on. And there was one hanging out way up there. Oops, a little over where x was 1 and y was 12. That's all the way up there. So that's not an I, that is a dot on the grid. And then we had 2, 6 and 6, 2, 1, 12. And actually at this point, what we're going to do is we're going to transition a little bit. What we're going to change to, because we want to make the pattern pop even more, it's going to be more visually cool this way. And these are all just experiments I've been doing. I'm sure there's a million ways to demonstrate fun ways we could incorporate the factors. And always feel free to try and think of your own experiments to do. It's good for your brain. But that was one way I was fiddling with it. But the main way I was fiddling with it was more so that, let's say that this is more of a times table. And let's actually put it, even though not everyone likes it when it goes downward, we're going to put it so the numbers grow in size from this corner, sort of like times tables have done. You know, multiplication tables that are often taught in school that are kind of boring if you try and memorize them, but have a lot of secret patterns in them. So we're going to imagine there's a big old times table, and these axis lines are now not a thing. This is just a big times table. And so like this is 1, 2, 3. I'm not going to write them all, but 5, 6, etc. 1, 2, 3, 4. So we have this big times table of like what multiplies against what, going down with these numbers times another axis of them. And now their blue lines aren't anything. They just happen to be on there. So we're ignoring the other axis lines. So if I now want to say what points are factors of 12, it's filling in squares on this. Really what it would be is if I wrote in every number on the times table, where do the 12s appear? But what we're doing now is we're not writing in all the numbers. We're just going to color in the square where the 12 appears. 7, Oh, that's weird. This is 13 out. Oh, I drew that dot too far because it's actually 13 out. I didn't expect that. I eyeballed it and I was like, it's probably 12. Should have looked more carefully for the baker's dozen. So that's our marker of when we are 10 this way or 13 that way. So their blue markers don't help us that much. But what we have here for 12 is we have 1 times 12 will get filled. And that gets filled here too. 1 times 12. Now remember, their blue lines you got to ignore so we can see that, oops, that these spots are symmetric, like in terms of they actually are the same amount apart, although they're different amounts on the blue. So then we get our 2 times 6s and our 3 times 4s. So 2 times 6. So here is the more full shape we get from 12. And now we can really see kind of that arc going. But what this is sort of on its first level is kind of like a factor finder. Like if I just had the times table and did this on all the spots, say 12, then I know what 12's factors are. I can read by either axis. You just have to choose one. If I choose this is the axis I'm calling factors, then I see 1, 2, 3, 4, 6, 12. And if I choose this is it, I'll also see those numbers. You just got to pick which one's your axis compared to the other, but it's the same because of the symmetry. And so we're going to say if we name factors, we're looking downward and seeing which rows it hits. So here this hits 1, 2, 3, 4, 6, and 12. Yep, those are the factors of 12. But now, what if we take this a step further? And this I haven't fully experimented with. This thought just hit me last night and I just started drawing some little shapes. Was, well, why don't we plot the dots that line up with all of the factors of 12? So this located 1, 2, 3, 4, 6, and 12. What if we colored in all those numbers' appearances on the times table? So going downward, 6's appearances are 6 times 1. So we're now coloring in all the factors' appearances of 12. 6 times 1 and 2 times 3. And here we get our other 2 times 3 and our other 6 times 1. Then we're going to add our factors of 4 and 12, our factors of 4 on their own, because we can make 4 with 4 times 1, 2 times 2, or 1 times 4. Now we can make 3 with 3 times 1 or 1 times 3. Make 2 like that, and we can make 1 like that. So we end up with this whole corner filled. We got a whole solid chunk at the edge because 12 could divide anything up through 4 and could even divide some combos of them, like 2 times 3s and 2 times 2s. So now look at that cool shape we get. So that's just 12, but what would happen as you expand it to higher numbers? Well, theoretically, we could try and fill in what 24 would contain from here, because this is part of the web 24 would have if we go that iterated level where you're finding all of the appearances of any factor of the number. So like if I go to 24 and not all this is going to fit, then we're going to be able to like add on to this. And this covered all of the smaller factors of it, the ones that 12 had. This doesn't cover 24 itself, and it's not going to cover one new factor that's going to emerge from that. So what we have now is 1 times 24. If that was 13, that's 20. I think that's it. And that doesn't fit here. You're going to have to imagine it. There's another one down there. And then we get 2 times 12. That one's kind of extending out from the wall. we get 3 times 8. 3 times 8 and 8 times 3. We get 6 times 4. And those are the factors of 24, but also, if we're playing the iterated game, that would have introduced 8 as a new factor that 12 didn't have. And so we need to find the ways of building 8 too, which is 1 times 8 and 2 times 4. And 2 times 2 times 2 isn't really a thing here. That's covered by 2 times 4 because it's just writing 2 variables on them. And then 1 times 8. So this is all of the spots where any factor of 24 lands. And if I picked a different number, like if I pick like 30, I would have to restart because that's not going to have the 4s, but it's going to have 5s. So other numbers will have different shapes. Now, also, how many dots get colored in is a good question, because on your first thing, which is the number itself, how many appearances does the number itself have? We've already looked at some patterns in that, such as it will only have an odd number of appearances if it's a perfect square, because that relates to the diagonal. Now, odd, remember, is like the opposite of even. So it's a relationship to, it'll have an even number of appearances of the number itself if it's not a perfect square. Well, I'm still researching this to confirm all of the details, but from what I was briefly looking up to see, I couldn't find this drawing anywhere online yet, although it might exist. But I found a list of a sequence that's going to be very related to this, which is adding up all the divisors of the divisors of a number. And that should end up being similar in this case, at least, because if we count all the divisors of all the divisors, well, it is a divisor, and so we have its appearances, and the others cover their own ways of making themselves. So I'm still looking up with that sequence to confirm this, but all I'm going to say for an interesting little sneak preview is that if the amount of appearances itself, just the amount of factors a number had, related to evenness and square numbers, well, it looks like the amount of appearances this iterated version contains relates to cubes and threeven numbers. So get ready for that in an episode at some point. Now, it also has some similarities, the shapes you get here, to a few traits of numbers. One thing that is a notable type to mention here would be highly composite numbers, because those are numbers with more factors than any smaller number for their size. That would mean if I just played the first level of this game where I'm just coloring in the number itself, not all its factors, highly composite numbers can be phrased as the numbers that for a given grid size, like 24 by 24 or whatever, have more factors than any, or have more dots they would make. If you're just coloring in them and not all their factors, than any other thing you could choose for that grid size. Another thing that will come into play is that certain types of numbers will be good at not having gaps here. Like if we went up to a good factorial, we would have a pretty good stretch here where the corner was all filled in. But if we ever have numbers that are things like the trait known as being 3 smooth, meaning numbers that only have prime factors of 2 or 3, and they could have a bunch of those 2s and 3s making them up, but they don't have any 5s or 7s or bigger in them. Just a bunch of, they could have 6s because that's 2s and 3s, but multiplicatively just 2s and 3s. Those would definitely be just missing a line here. It has a gap on the 5, like this one. That's 3 smooth. It's 2 times 2 times 2 times 3. Now, we'll also think, uh-oh, my internet might be acting weird. Hopefully it's working. But how many of them can be, or that, like in this case, 24, it has a lot of sames. This is 2 cubed times 3. And so that has 4 different prime factors if you count all of them, but 3 of them are all the same type, all 2s. And that's going to create a slightly different appearance of your web than, regardless of what the numbers are, the primes making it up, if we had like 4 factors being 4 different primes or something. Now, like, what's similar about the numbers? Now we're just going to write on the back for a minute. What's similar about the numbers 24 and 54? Not that they end in a 4. That's not it, by the way. And similar about those and even 50. That is different between those and 30. Well, you could try and figure out like they're made up of different types of things, but that's not going to be the distinction. This one's made up of 2s and 3s. This one's made up of 2s and 3s. This one's made up of 2s and 5s. This one's made up of 2s, 3s, and 5s. So it's not really what they're made up of that's putting some in some camp or not, or the other. It's how they use their combo. So 54, 54 is 3 cubed times 2. And I'm just going to put them in parentheses so that people know it's multiplying without weird stuff. Here, 24 was 2 cubed times 3. 50 is actually 2 cubed. Oh, no, I messed that up. I wanted to put 40 here. Sorry if anyone was somehow able to spot the pattern. Still contains 2s and 5s is the one I meant, because here we have 2 cubed times 5. 50 would be 2 squared times, 2 times 5 squared. But here we got 2 cubed times 5. So what these numbers were on the top line, we had ones that had some prime cubed in their factorization and another one hanging out singularly. This one had a 2, a 3, and a 5 each once. This had 3 single separate ones. Now, they're not all going to have the exact same amount of divisors, but I can do a calculation that I want to show you guys this trick in a cool episode coming soon. But essentially, we can figure out once, I'll show you this trick pretty soon, but I can deduce that the top half has 8, and so does this. So these, that was why these came to mind, is that all of these have 8 factors, all these numbers, 30, 40, 24, 54. They all have exactly 8 factors. However, they're using them in a different way. So if you made a list that was how many divisors a number had, you'd have a more clear distinction than just primes versus composites versus 1. But you'd still have all of these on the same one if you said how many divisors they have. Yet there's going to be ways in which the pictures and interactions of the dots of these could be different than the ones that are like this. And this is actually condensed mathematically into something known as a prime signature. And I'm for sure going to make a full episode about sometime. And the prime signature is just reduces to not caring what primes are in your thing, but caring about what amount of different types there were. Did it triple any, double any, how many singles are there and stuff? And so here, for example, these ones, if we're using not ordered ones, there are an ordered type, but just on the typical type of prime signature, we can just say that there was 3 of 1 and 1 of 1. We're not ordering bigger or smaller number. And all of these fit that prime signature, whereas this fits this prime signature. So this is a hyper 11y prime signature. So think about that. What would it mean to be hyper 11-like in your prime signature with a bunch of ones? What would traits be of other types of prime signatures? So like a prime, its prime signature is just 1. But what would it mean to be other prime signatures? So I'll show a lot of cool stuff with that in an episode topic soon. So that's all for the graph paper for a minute. I guess I will open the bigger whiteboard in case we need that in a moment. Like I said, feel free to ask any questions or leave your thoughts in the comments, because we're also doing a little I'll be trying to be extra responsive to the comments today, because I called it a Q&A because we hit 70,000 combo lords. Pretty awesome. Got to mention about quaternions. Yep, those are cool. I think I'll have to teach more of the viewers about complex numbers before we get to quaternions. And I want to visit the bridge where they were originally etched into a bridge by the mathematician who discovered them. So now I don't think the original etching is there, but they have a plaque in its honor. And maybe I'll somehow find a way to take a really far field trip to the bridge that quaternions were established on in their invention to do a quaternion video someday. Hey to all the fans, hey to the magic fellow there and all the others. And someone's saying, as we approach infinity, it will look like an inverse exponential function. Well, that will depend. If you mean on the ones where it was looking swoopy, some types of number, if we're just graphing dots, will look more and more dot-like. But a prime would only have a few appearances. What grid spots can multiply to 13? There's just going to be 4 of those, even if you count the negative symmetry, and only 2 if you count the actual factor zone in the positive axis. So depending on the number, as you go big, you could get a ton of dots that look like a super swoopy shape or get not much. And that relates to the prime signatures, because other numbers that wouldn't get very many, for example, would be a number with a prime signature of just a 2, which means essentially a number that's a square of a prime. So like a square that can't be factored apart from that. And ones that are 1, 1 in their prime signature, semi-primes. Well, no, those are square-free semi-primes. So those are sort of the complement of the 2 in the thing, although they have different traits. One has 3 factors, one has 4 factors. But there are certain prime signatures that won't get very many dots for a number like that. And whoever caught the stream for the first time, welcome. And I will get on a more dedicated streaming schedule at some point. It's been quite a crazy couple months and year, so still just making things work a day at a time, and it's somehow working, but we will get on a consistent schedule at some point. I also do have to do a reminder here that if anyone wants to join on some group type classes that I'll be doing with smaller groups to teach things that I'm currently studying and some extra clarifying topics and where people could talk to me more directly, that is one of the higher tiers on the newer Patreon that I made. There are also lower tiers where I'll be thanking people's names and giving a bunch of cool bonus videos and stuff. So just to mention, that came out a few days ago. Please consider checking it out. In fact, I will be thanking the names of all of the current patrons, whatever you call them, Patreon supporters, probably in the next stream once it's been up for a few more days. Normally, I'll just be able to thank people of some of the higher tiers, but I'll be thanking all of them at some stream soon, just to be extra thankful for all of the early people on board there. And who asked if I've studied analysis, not a huge amount. I mean, I've read books about it, but I'm not super adept on it. Depending the type you mean, though, analysis is a very vague word. If you mean complex analysis, was sort of along the lines I was thinking, because we were talking about that. Complex analysis, I'm not like a master at by any means, far from that. But analysis is a pretty vague word, so it shows up in many fields. Let's see. And someone's wondering what level of math education I have. I didn't take like a 4-year degree or anything, so I didn't really keep track of exactly how many college classes I took in it. I took about 2 years worth of college that were mostly math focused, mixed with other stuff. And I did really good on it in high school, but I've learned a lot more on reading books, which I'll whip some out in a minute. I have all sorts of my books here, and doing my own experiments, reading online articles, trying to find other mathematical people to talk to, and things like that. So most of my math knowledge didn't come from school, but I guess you would say I went through a couple years of college. But I didn't end up going to the nicer colleges that accepted me, kind of for money reasons, among other reasons. So I chose other pursuits of learning. Someone's wondering, they posed a question that could be fun, which is how many zeros would be at the end of 100 factorial? Now, that is a good question, and maybe that will come up in a video. We can kind of give a clue right now, because I think that to do how many zeros are at the end of 100 factorial might take me an extra level of like tool to use on this project that I would have to think through about what the second half of how to do. Like, for example, 1,000 factorial would take 2 steps. The first step is to figure out what types of number are contributing to zeros, and that step I could figure out just reading that right here. So with that, why don't we look at like how many zeros would be at the end of 20 factorial for fun? And then if anyone wants, they can try and do 100 on their own. And maybe I'll put that in the next factorial centered episode, or the next episode that relates to zeros of some sort. So what contributes to a zero? What's a zero in a number? Well, we're in base 10, so a zero in a number means you had a factor of 2 somewhere and a factor of 5 somewhere. So if we add each factorial and we were keeping track of how many 2s and how many 5s there are and pairing them up, we're going to be finding our zeros. However, we'll quickly see that there are way more 2s than 5s. Every even number contributes at least one new 2 in the prime factorization thrown into the factorial. 5s are thrown in way less often. So there's already going to be a 2 ready to pair up with each 5 when we have this bigger mess factorial and we're wondering what primes make it up. So really the question is going to be how many 5s there are. So we get, at this point, well, let's say 25 factorial. That'll be slightly more interesting. 25 factorial, we're going to get 5 factorial is going to give us a 5. We already have a 2 to line up with that. 10 factorial is going to give us a 5. 15 factorial will give us a 5. 20 factorial will. And 25 factorial is going to give us 2 5s. So I believe 25 factorial should have 6 zeros. Let's see if that's correct. I'm going to pull up Wolfram Alpha. That is a pretty good online calculator if you ever need. They also have some good pages on there describing certain math concepts, sort of similar to Wikipedia. So let's see. 25 factorial. 6 zeros, nailed it. So yeah, to me, it would be how many 5s you get. Now, for 100, that would mean it would be pretty quick to figure that out. So someone can try and figure that out and comment it if they want. But I think you'd need an extra tool to figure out if you were to do like how many zeros are at the end of 1,000,000 factorial or something, because then you'd have to say, how many, how many multiples of 5 under that each give you 1, but some of the multiples of 5 give you 2, some of them would be giving you 3, because like the number 125 factorial throws 3 5s in the mix. So yeah. We got another lover of the Wolfram on there. They are great. Let me give a little recommendation for some sites that are good to anyone who wants to be doing a little math research on your own. You got Wolfram Alpha, and there's one called Wolfram Math World, which is a sub portal on there somewhere with those articles I was talking about, where you can read about different concepts. Not as much info as Wikipedia, but maybe a little more airtight. Maybe Wikipedia's math stuff is 99.5% accurate, and this is 99.9% accurate. I don't know the exact stat on it, but maybe a little more trustworthy. But usually Wikipedia is right too. You do want to double check it, but it's usually right too, for math stuff at least, not necessarily for like people's biographies or stuff. You definitely want to know the OEIS. That is where I found the sequence of how many factors of a number's factors are there, and found that it seemed to relate to 3 evens by analyzing the OEIS. So this is the online encyclopedia of integer sequences. High-tech people, I mean, not high-tech, but people who like flashy technology might not like it that much. It's very text-based and old-fashioned looking, but has a lot of good info on it. Also has article-like thing, not like articles, but pages that are Wikipedia-like, or like this Math World on there for certain things, where they not only have a little description of them, but they have all the sequences that are cataloged in there that relate to them. That is a classic. Shout out to Neil Sloan, who originally invented that. Then you're going to want to sometimes, to find new topics, go on Wikipedia. See what Wikipedia has to say about the topic you're into. And even if you're skeptical about whether you can trust the knowledge or whether they're missing anything, you're at least going to see a lot to think about, a lot of possible topics that it might relate to, or that you might also be interested in. And you're going to want to know, if you want to graph some cool shapes on a graphing calculator, you're going to want to know Desmos. And one last one is that there's a forum called Stack Exchange, and it's something like math.stackexchange. I don't know exactly what it is. That has some of the smartest people talking back and forth in a public way you can find. A lot of cool questions being answered in an actually very smart way on there. So these are some good websites. I'm very sloppy. If you want to have some fun, sometimes you go into a paper and on the second paragraph, they're talking about a term as if you should know it and you don't know it. And you're like, better quit while I'm ahead, but still good to try. So someone's saying that, let me scroll up a little bit. Someone's saying, is there no solution for things like square root of x is -1? And that would be I. Well, wait, square root of x is -1. Wait, no, square root of -1 is I, but square root of x being -1, x can be 1. So the square root of 1 technically is both 1 and -1, but often it makes sense for mathematicians to just talk about what's called the principal or primary root of it. So typically, yeah, the principal square root is going to be, in that case where there's a positive and a negative, the positive is going to be the one that gets that title, principal. And that's the one that gets referred to. But there are technically another square root of 1. Now, a common misconception is that when you write square root of 4 or something, some people think they're being all smart by saying that, nope, that could be plus or -2. Nope, this symbol means the principal square root. So if you see that symbol, you only need to refer to the positive one if it's that type of thing where it's like a whole number in there, but it could be negative or it could be positive. You only need to refer to the principal one when you see that symbol. However, if we say that x squared equals 4, what is x? Then we want to say it could be -2 or 2. So that's a good one to remember. There's a secret square root hiding behind those. Now, some could have even more. Here's why that works. This is a polynomial with 2 as an exponent. And if 2 is the highest power of a typical rational polynomial, should have 2 solutions. And it's correct here. What does that mean if we had cubed? Well, I wanted to make a whole video about this, and I probably still will, but I'm going to do a really sloppy version of something really cool right here to show you. What if I say x cubed is 1? Well, when I said x squared is 1, we said it could be x could be 1 or could be -1. But now when I'm saying cubed, -1 doesn't work here. -1 cubed is -1. So it looks like 1 is the only answer here. But that doesn't make sense. When we say x equals 1, there's one answer. When we said x squared equals 1, there's 2 answers. Why would it go down to 1 answer at that point? It didn't. There are 3 answers to what x can be. 2 of them are hiding. So when we're doing here, what we're doing here is finding roots of unity. Now, what we're going to do right here is use this, but you're going to pretend that we're at a bigger scale. Each of these little points on here is 1/5 on this scale. So pretend there's a perfect circle and that this is 1 on each side. That is a length of 1. So for the radius. So when we said x equals 1, it was just there. When we said x squared equals 1, it was there and there. The original point and 1 equidistant to make 2 points equidistant on the circle with 1 being there. And it turns out if I say which x's can be, and okay, now we got to go further. So that was 1, that was -1, but now, sorry guys, this direction is how many i's there are. You know, I said someday this direction would be how many i's there were. Came quicker than I thought. So here we got the point right there is I, and the point right there is 1. The point down here is -I, and the point over there is -1. Okay. So if I say which x's can x cubed equal 1? Well, the reason it looked like it shrunk down to 1 solution is because we were just talking about the real number line. This line was enough to talk about all the typical real numbers. The other 2 aren't on that line. Squared got lucky that having 2 dots equidistant made it so that if 1's on the line, both are. But cubed, 3 equidistant dots would be like that. And now we're going to look up on Wolfram Alpha what those values are. And I'm going to look up if the cube roots of 1 pulls it up. And yep, cube roots of 1 pulled it up. And they have it phrased in a few ways, but it's approximately -5 plus about 0.866-ish I and negative 0.5 minus 0.866-ish I. And let me get a reminder of what its exact form would be. The exact forms are -1 half. Okay, but -1 on the numerator plus or minus I root 3 halves. So this is what they turn out to be. -1 plus I root 3 all over 2 and -1 minus I root 3 all over 2. So kind of trippy when you get 3 there. Don't worry, folks. 4 gets lucky and back to normal again. 4 is like a very definitive one. 4 dots equidistant on this circle give us these. Give us the classic ones. 1, -1, I, and negative I. 5, you get kind of weird again. So now how about 6? Let's think about what 6 dots on the circle would have. 6 dots equidistant. 2 of them would be the 3 dots from before. Remember how 3s had these were the cube roots. Well, if I had the 6th roots, x to the 6 equals 1, and the solutions to that, it would be 6 equidistant dots, and the 3 ones would be there still. They would just have one between them, because that's 6 equidistant dots now. And we do get one on the other side for that. 6 is pretty cool. Another reason 6 is one of the coolest numbers, you get 1 and -1 as answers to the 6th roots of, it's called roots of unity because unity refers to types of 1 in mathematics sometimes. The 6th roots of unity get 1, -1, and then these kind of weirdo ones. And in fact, 12 would be kind of cool because we would have one in between each of these. And so 12 would be like a clock-like one. And I'm probably doing this wrong, but we would basically have the classic 4 and these interesting 30 ones. 8 would also be pretty cool. So very crazy. The roots of unity, something like a polynomial with a bunch of normal rational coefficients and finite length. And in rational coefficients and finite length, you can expect the amount of answers as the exponent of the highest. Like if I have like, how many answers are there to x to the 7th power equals 100? Well, they're going to be pretty weird answers, but we could expect 7. And someone asked if I need a lamp. Well, okay, I will admit I was kind of phrasing it like, yeah, it doesn't seem that dark in here. But I realized that the main room light is dead. It's just hard to replace. I need to replace that. It's harder for me to do things like that because I'm still semi-recovering from surgeries. So it's like hard for me to get on a ladder and stuff. But I need to replace the light up there. So I have a smaller one over here. So I guess it makes sense that it is a little darker than sometimes it will be. Someone else asked how old I am. I am 29. I will be 30 next June, in the middle of grade -2. Not in the middle, about a third of the way through grade -2 probably. People have been asking if grade -2 has started. No. I'm just talking about getting ready for grade -2 because I need it to be extra dope. So I can't just, and I don't want to take a ton of time off. So I can't just do my normal grade -1 thing, take 2 days off and expect grade -2 to be cooler than grade -1. I got to start preparing that and then have grade -1 veer upward in craziness and coolness to meet grade -2 at its start. So Grade -2 is still a few more months. Still going to get a lot more grade -1 awesomeness, but we're getting ready. I, for example, showed a lot of dice that I had recently gotten, and there are some more. The mini ones were really cheap, and I like the mini ones, so we got a lot of mini ones. So these are good if we want to do like a big scale probability thing where we like roll a ton of them and count some trait about them. Someone said it's 2:15 a.m. there in India. Yep, different times all over. Thank you for being up to watch the stream. For me, it is just 12:45 p.m. And I will go more into this polynomial stuff in some episodes. I want to make sure I phrase it completely properly and lead you guys down to the coolest observations. So I'll have to explain more about what you know from odd valued polynomials and even ones. We go forward. Now, and someone's mentioning conjugate pairs. Yep, a lot of interesting stuff there. So thank you all for leaving your thoughts. And already kind of answered the studying question many times. Now, I guess I will note that since I always talk about that I read a bunch of books, and that's where I get a lot of learning from. I don't have all my best ones right here. Some of those are in the other room, but I can still take a look at a few of the things that I've recently been reading. Here is one I've already shown before that I highly recommend. Anything from this guy, Martin Gardner. Very fun puzzles and very cool, what you could call recreational math, in that he didn't really have the aim of proving a singular thing or doing like as much applied math. He wanted to kind of go problem to problem and share new findings about little things one at a time and present, combinations of other discoveries in cool related forms or new visualizations to the world and stuff. So it's very fun, a lot of different like game like puzzle like things in there. And then here's one I've been reading that's cool. So this one I'm still reading, but it's cool. It's all number theory, very dense, but a lot of interesting stuff I learned in this one. This one, like some books that I bought a bunch of books about number theory, just the ones that were cheap without looking much about them. And some of them I did already know most of the stuff in them. This one, there was a lot of stuff I didn't know yet. And what else? Okay, this one's okay. So I had a book called The Dictionary of Interesting Numbers, and it's really cool. It's out in another room. In fact, it's in the combo class room, but it is locked up from the rain. Although it already got rained on a little, but now it's not getting rained on anymore. But the Dictionary of Interesting Numbers was awesome. And I was like, do they have more things like this? And I'm sure that this isn't the only interpretation of what numbers you want to include. I surely have other ones I would have added if I wrote the Dictionary of Numbers. And so I looked up if there's other like Dictionary of Numbers. And that first one was like, obviously like kind of like how a dictionary has a definition with it. It has like the trait that they found cool about the number next to it. But I ordered another Dictionary of Numbers. And guys, it's literally just the numbers. So at first I was like, what am I going to do with this? I didn't know I was just buying a long list of numbers. And I was like, okay, I've got to be able to find some cool patterns that this book could help me demonstrate about numbers somehow. Now, it's not going to be like our times table thingy because this isn't structured times table like. However, it might be like a modular chart to some degree. Now, every page, however far you go down the book, had the numbers in 8 rows. They did put one getting a head start, But that doesn't change the fact that they're cycling in 8s. So we can see that since 1 got a head start, the multiples of 8 are the second last row. But these are the multiples of 8 in the second last row. That this column is the numbers congruent to 2 in mod 8. This is the numbers congruent to 3 in mod 8, and so on. This is essentially what they're congruent to in mod 8, except this one you'd put the 1 on top, and this one you'd call 0. So we have a slightly askew modular table that would still work. What does that mean? Well, I'm going to save this for another episode so I can actually write in the book, because I am going to write in the book to show some patterns. But what I want avid viewers who have seen some previous episodes to think about is what patterns might be observed if I were to highlight or circle or whatever all the square numbers. What other patterns might emerge if I were to highlight or circle all of the primes? For example, would either of those have members in all the columns at some point on some page or another? Or would they be missing columns or rows, or what traits would they have? So trying to find a silver lining out of this, guys. I actually think that now that made me think of something that I'll make a video about related to it. And just because it made me laugh, I'm going to rank this book a B grade. I'm not going to give it a terrible grade. I think it's a B grade book in concept. You definitely don't need more of them. It says on here that more volumes will be published soon. I really hope he's joking, because the first one's funny. But if he tries to get away with publishing a second one of these, I'm not buying that. It also cuts off at a really arbitrary point. It lists all of the natural numbers from 1 to 49,149. Great. So, yeah, that's a book that I will be studying, but I'm going to be putting in most of the effort with that studying. It still was a really good exercise that I'm still going through. What patterns could I get out of this? So sometimes it's like, if you got to paint with not that many colors, you got to be really creative. And sometimes you make a cool painting because of it. So I feel like I'm going to make a really creative video out of the limitations of this being an off-centered mod 8 table. And I don't know what else I can get out of it, but I'm going to make that off-centered mod 8 table show a lot of cool patterns. So there's that one. And then there are other books. I have all sorts of books on my bookshelf there. A lot of good ones. A lot of them are not in this room, but are in the other room. I also have a lot of notebooks on here. A lot of my own personal writings. I'm going to make sure that I got to look through those before I show them to you guys. But like one example of how I like paper notebooks. Here's one of a paper notebook I have. I'm not going to show it until I see what's on a page, but an example of how it can be good to work on paper notebooks sometimes instead of just online is sometimes it's useful to work by hand and do some of your own investigations. That was for a chart for a card game I was working on a while ago. I'm going to cover up the instructions, but see if you can figure out what the heck I might have been doing there. But yeah, sometime I'll find the notes that are worth sharing and I'm able to share. So yeah, a lot of good books there. Reading is useful for your brain and it's fun. It can be meditative. So hope people get into reading. And if they're not into reading, hopefully you will at least get in. I mean, hopefully you'll get into reading if you're not this year. But if you're not, hopefully you'll at least try it out when I publish some books someday. I'm going to find a way to self-publish just by having followers here and just trying to work with someone who knows how to print books. Because now that I'm building a combo class world, maybe I don't have to work with any dumb publishers to publish my math books. Maybe I can do it myself, but we'll see. If any publisher wants to take my math books, I'm still listening. So someone said, good to reference if you don't know the number before 70. I'm not sure when 69 came up. I know it's a quite memey number. I forget when that was being talked about here. Yes, the book that listed all the numbers. Yes, well, 69 is so popular in our culture because it is the only number whose square and cube between the two of them contain all decimal digits once each. And that's why it's popular in our culture. Just like 420 is popular in our culture because it is the smallest number that is divisible by all of the integers 1 through 7. So, just in case nobody knew why those were popping off in our culture. And if you want to know why people are scared of 666, it's probably because of its cool math traits, because that has a lot of cool math stuff about it. I should have been on the Grammy ballot. Well, I haven't dropped my music for you guys yet. I've maybe some of the followers somehow dug up my music. I will be posting it for at least my Patreon followers soon, and then for other people at some point. Music I've dropped in the past, which is under various names. So maybe some people have found some, but not others. And then I will be dropping the first music under the Demotro name at some point, because I do make a lot of music. So maybe I will be on the Grammy ballot once I've actually dropped my music. Not that I care about awards, who cares? If I make something and I'm proud of it, then that's okay. I will feel like it has done good things for the world and I've achieved what I wanted. And as long as a bunch of people are banging my music, I won't care if it is on any ballots or not. Although it'd be kind of cool to show up to the Grammys in this lab coat. Do you think they would let me in if I wore this lab coat, or do they have like a policy against that? They're probably so like corporate Hollywoodish they wouldn't let me in with the lab coat. So that would maybe be some good press. I wouldn't go collect my award because I insisted on wearing my lab coat and they wouldn't let me in. Maybe I would show up on fire. We'll figure something out. That's fun. Yeah, Jack Harlow's all right. I listen to a lot of hip hop music. He's all right, but there are better rappers out there, such as me. If anyone sets it up, I will beat Jack Harlow in a rap battle. You might think I'm joking, but I have practiced freestyle rapping in the past for a countless amount of hours. And in a freestyle rap battle against Jack Harlow, I will win. And I don't mean that as a diss to him. Like, he's not terrible or anything as a rapper. He's all right. There's some good songs he's made. But I will beat him in a battle. So someone set that up. Someone said, what name will I release books under? Great question. Now, maybe under my real name, which my full name is a little different to anyone who hasn't watched the credits of my full combo class episodes. My birth name is Dimitri. I just go by Demotro when I'm doing my videos, and I've fallen into that persona quite hard. So, technically, legally, I am Dimitri, not Demotro. Although I do like when you guys call me Demotro, because that is sort of my teaching name, at least, and has become sort of a pretty major nickname for me. Now, I have to wonder whether I'm going to publish it under my real name or whether I will publish it just under Demotro. Normally it's kind of an aggressive, cocky thing to try and get away with publishing with just a one name. Like, it's like, who does this guy think he is? Plato or something? Like, who goes with one name. Some people get assigned that now. Like, you have, what's the name for that? There's a term for that when you have a one-word name. Term for a one-word name for a person. It's called a mononym. So yeah, like, be kind of a cocky maneuver to try and publish a book under the mononym Demotro. But I might just do it. There's not any other Demotros publishing books right now. This channel, technically, I had to claim a handle, is the new way they're doing URLs for this channel. The old channel was in time to get, the main channel is in time to get just being /combo class will take you there, like YouTube /combo class takes you to the main channel. But this one, you would need an @ of some sort, like books or something like that, is way too long to put in a URL. So the URL of this page is youtube.com/@Demotro. And there's a chance at some point, once I've put out more music and other projects on here, I will name this channel Demotro. But it'll still have the same math-related stuff a lot of the time, because that's what I love. Really remember that the main channel is where the deepest combo class learning and lore is. But this channel, and if you guys love the shorts, I will be making more of those. And yep, Quinn has found the one of the albums I released as a group with my friends. Now, that is one of many things I've released with my friends. That's just the only one that was so publicly available on certain sites. So that will probably be one of the first ones I'll pop to everyone else. Thank you to everyone for all of those comments. And why don't I unwrap the big whiteboard? But we might not need it today. I'm not sure how much longer we're going to stream today, because the main thing I wanted to do a little thinking about is what sorts of cool shapes happen when we find the factors of the factors of the numbers. And if anyone makes any of their own, feel free to send them to me. You can find my email on the contact page if anyone makes any cool little grid arrangements of those for different numbers. Now, remember, you're not necessarily going to need to include primes, because those would be so minimal that you're maybe going to want to either just run through the composites, or even certain types of number, like do the first few factorials would be cool or something. Highly composite numbers, of course, are a good one. As well as, if you look at this list called the superior highly composite numbers, those like add on one new prime factor to the last while keeping the old ones. So that would be a growing web, sort of like the factorials. You could also try the primorials, although primorials will be missing they'll be missing a line at the 4, for example, because they only get each prime once. Someone says they're finding some interesting stuff with the x to the n minus 1 equals 0 series. And to note to anyone who didn't make the translation, that's the same as when I was saying x to the something equals 1. That's just it with the ones shuffled over. And yeah, so like x to the 7 minus 1, they said where the solutions were a little trickier on that one. And yeah, 7th powers sometimes can be a little weird. You get some weird stuff with 7s once in a while, like the regular heptagon is the first regular polygon you can't make with a straight edge and compass. And let's unwrap this, but I think I might only hang around a little longer. I got some stuff to work on for later. And I need to try and check on my classroom and see how much chaos the rain has been causing out there. Although sometimes we may have more streams in the room if it's a rainy week, so we shall see. And remember, I am open to the idea of writing cool equations on the walls so people can remind me if they ever think that an equation that I mentioned or that's on their mind, I will maybe think notable enough to write on the wall. Don't know if I'm going to write one right now because I don't know where a permanent marker is. It's better than dry erase. Although dry erase works well enough on there. Now this could also be hung up. Theoretically, I could hang this on the wall. Although that would actually be bad for streaming. To it on the wall over there. It'd be like the worst place on the side of my bed. It also looks like it came with something magnetic here, if that's what this is. Yeah, we got some magnets to clip stuff to it. That'll be handy. In fact, if you ever need a double trouble graph paper where we clip on graph paper on it, although that might be heavy enough to slowly slide this down. Yeah, it's like sliding. But if I use normal paper, it would work. It's just a little too heavy for the magnet because it's actually a whiteboard sheet of its own. I also saw that they make tape on whiteboard stuff that you can put on your walls. That these walls might be kind of bumpy, so it might not work great, but maybe I'll just get a bunch of that tape on whiteboard stuff at some point, and then we can just make more zones whiteboards. Turn random things into whiteboards. All right. I think that's all the comments. So we got our new whiteboard here. That's nifty. We get the magnet back on it. I knew it would come in handy, and it already could have come in handy today because I'm trapped in the room. So if I need to do anything today, my other whiteboards are outside. Now I have this whiteboard, and we could draw things like an approximation of what one of the shapes would look like. Well, actually, here's what we're going to do. We're just going to use the top here as our corner. And here's what we're going to do. Let's pretend there's a big one of those times tables from before. And we're going to do 5 factorial, which is 120. Now, to make sure I don't miss any, I'm looking up all its factors. So if we did that game earlier, now we're going to be first just showing the appearances of 120. So the appearances of 120 are 1 times 120. We can put it all the way out there. And similar amount there. 2 times 60. 2 times 60. This is just going to be really approximate. And then we have 3 times 40. 4 times 30. So yeah, 3 times 40, 4 times 30, 6 times 20. This is not exactly how it would be. 6 times 20, 6 times 20. Oh, we also had 5 times 24. 5 times. So we would get something like this. We'd get a bunch of them. 5 times 24. And then we get 30 times 4. That's all of the ones for that itself. We have 10 times 12. So that one really gets a curve because it's big enough and has a lot of factors. 120, known as the long hundred before. Remember, we got to bring that term back, start using the term long hundred. 120 is a very important number. And pretty soon we'll have the long hundred on our list along with hyper 11s and 3-vins on things that you keep seeing everywhere. Because I keep seeing it when I'm researching videos. It's all over. It's a cool number. It's 5 factorial. It's also highly composite. It's a lot of stuff. So that would be what we would get from that. But what if we plotted some of the other ones? Now, this isn't going to be exactly what 120 does. But the other ones, like, remember when I was feeling like they make certain like little like walls that come out and hop off at certain points. This isn't 120, remember? This is just like what some of them look like. They have this like shell right there that like fills in at first and then has like little gaps and like little hollow things. And it makes this like cool little symmetrical weirdo thingy that's like filling in there if you fill in all the appearances of all the factors. So that's something I will make some cool visualizations of at some point. But 120 will take a minute, but be worth it. So I think that I'm actually going to wrap up pretty soon. One of the last things we'll end off with, unless I get carried away on anything else, is, although hello to the new person here, that one last thing that I recently got when I ordered the whiteboard and all the dice is, well, by some standards, you could call this that I bought 20 more clocks. However, some would call it quite a stretch to call these clocks. What do you think? Could you argue that these are clocks? Hourglasses? Well, I'm going to need these for a video before long. And I'm still going over in my head whether these are secretly clocks, maybe. Who knows? Don't worry, I won't count them all toward my clock quest number goal. But yeah, I don't know how accurate they are anyway. I think they're supposed to be a minute. We will try them later. Those will probably come in handy. And luckily the rain did chill out, so theoretically we could even visit the combo classroom in a minute maybe. Let me see what the weather's looking like. Let's see. It's looking forecast to rain for many hours, for the next 8 hours. So never mind. We're not taking a field trip outside. But in any case, if I log off in a moment, super awesome. Thank you all for stopping by to this live little math lesson stream. We'll have some more shorts and bonus lessons and stuff coming soon, and a snack break episode on the main channel next week. Make sure to also check out the links in the description, like the Discord, where we hang out and chat as Combo Lords, the subreddit, which needs more cool stuff on it, and the Patreon that's new, and I would love if you took a peek at that. And you are all super awesome. I was going to shout out the names of some of the people who have supported on Patreon here. I'm going to do that next time. Probably, even though usually that will just be for higher tiers. I actually edit it after to say that sometimes the lower tiers will also get that. Yeah, so as Quinn notes, I can tell a time with them. But yeah, it's maybe a different form of, like, a stopped clock is right twice a day. How often would you say those are right? Once per turn or twice? I don't know. Interesting. Yeah, so thank you all so much. We will be back for more wild mathematical learning soon. And if for some reason the rain clears up, I may film out there later today again. But stay tuned for a lot more fun. I will chat with some of you in the Discord later, and hope y'all have a really good one.